So just to introduce myself, so I'm Hammond. I work out of Sandia National Labs down in New Mexico. And this presentation we're going to split in half. So you're going to have me for half the time. We'll go to sleep. The most exciting piece is going to be from Pritchard from Los Alamos, and Howard will be up here in a second. So although you're just hearing from Sandia and Los Alamos, I want to emphasize that we're working with lots of our colleagues at Lawrence Livermore. They're very busy working on some other machine stuff right now, and so they're down in California doing that. But some of this work is representing some of the stuff they do as well. So let me just start by saying I think it's a really exciting time to be an HPC. I wish when I was sat where you guys were about a decade ago, it was as exciting as it is today. It was pretty boring then. We just kept buying Intel processors. You'd wait the next year and another gigahertz would be added and another core would be added and everything would be fantastic. And our apps teams were really happy. So what is it that's making it exciting? So you're hearing a lot about exascale computing. Most of you are probably here to talk about that. And there's just some amazing stuff going on there. There's lots of competition across the world. If you work in the kind of space I work in, we agonize, will the US lead this anymore, or will China or Europe or Japan come along and lead it? And so we're desperately busy trying to make sure that we have the best machine. And you heard from some of the guys at Argonne and Oak Ridge today about how we're trying to do that. There's the rise and adoption of machine learning and AI. I expect some of you are even here to talk about that. This stuff makes me groan a little bit because it's all completely new to me. And there's lots of frameworks. And this stuff's really hard, right? We're still trying to figure out how to take machine learning and make it work in HPC. If you work in HPC, it's not a slam dunk that this is all going to just work out of the box. It's quite complicated. And the bit that I'm going to come and talk about today is this sort of new hardware and software. So as we pile money into these exascale machines, billions of dollars across the world, we don't just want to keep going with the last hurrah for technology that's sort of dying out. We want to do new technology. We want to bring new things to the HPC community and accelerators and GPUs and other FPGAs, other technologies that will basically take us forward for another decade. So we're going to talk a little bit about ARM today. In some ways it's new and in some ways it's old. We'll talk a little bit about what that is. So what we'll cover today is kind of why is ARM interesting? Why should you really care about that? Why are we spending a load of money caring about that and not just buying more x86 processors? Okay? That's kind of an interesting question. It's one that I get asked a lot and I have to go defend it. So hopefully my well-rehearsed answer will convince you. So you'll tell me in questions if I don't. We'll compare some of the differences, and I'll talk to you a little bit about what this Vanguard program is we're trying to do at NNSA. So for those of you who don't know what NNSA is, it's the nuclear deterrence component of the United States Department of Energy. There's 3 labs, there's Sandia, there's Los Alamos and Lawrence, and we all are friends, and we all work together to make the nuclear deterrence safe. Okay, so we spend lots of money on computing and lots of time trying to make sure that that's the case. And then we'll do a split here, and Howard will come up and talk to you about the sort of meat of the presentation, some of the application performance results that we're seeing and why some of that's interesting. And as we move forward, what some of the new changes in the ARM processors will bring to us. There's a tiny little section at the end on porting to ARM, but if you guys are going to go do this, that's the slide you want to go see. So if you're watching this on the internet about what do you need to do to go run on ARM, scroll right to the end and look at that last slide. Okay. So what's so interesting about ARM? So for those of you we talked about Top 500 today. I think lots of the speakers that came before have talked a bit about what that kind of collection of results is. So this is just years across the bottom here, okay? And then the area graph is showing you loads of different instruction sets. So 1 million years ago, when people like me were at grad school, we were looking, and you could go out, and the shopping list for instruction sets was huge. It was a complete nightmare. So you'd go out and you'd try to find the best processor, and you'd scroll around, and somebody would say, oh, you should buy a Sun processor, or somebody would say you should buy an IBM processor. And there was loads of things to choose from. Today, it's sort of go down Best Buy, and it's what everybody else is buying, right? So why is that the case? Well, it's this huge red thing here that became Intel, and the little bit of yellow up there that's AMD. They just took the world over, okay? So in many ways, it's just, if you think about processors, they're just instructions. They just run stuff. As long as it can compile Fortran and C and C++, who cares, right? Well, in other ways, it is interesting. So ARM is an interesting exercise here. It's new. It's different, right? You don't go and buy an ARM processor for an ARM, although you can do that. what you do is you go buy an ARM-based processor from somebody else. So I develop the instruction set, I write the compilers, and I give it to this guy over here, and he goes and he implements a processor using the instructions. And he can kind of mix and match stuff for his type of processor. And over here, this lady might go out and she might implement something special for her ARM processor. So it look completely different. So if I go out and I say, I'm going to buy an ARM processor, it's kind of which one, right? There could be, every one of you could have a special version of a processor that works just for you. So if you happen to be at DOE and you've got a very complicated workload and you want a special processor that's just for your workload, we might be able to find something sort of special, right? So I don't have to go down Best Buy and buy whatever everybody else is buying. I can be the special flower in the room and I can have it just for me. Okay, so it's kind of cool, right? That's what I'd like to be able to do. And at the same time, if I don't like what ARM is doing, but I want to put something else in there, I could maybe borrow some intellectual property from somebody else. So I could take something from ARM and something from somebody else, and I can squish them together in a processor, and maybe that's even better for my workload. So we're kind of interested in that. I think a second reason, but one of the reasons we worry about a lot, is DOE invests a ton of money in computing. You're seeing all these swanky pictures from Argonne and Oak Ridge, and you'll see some from other labs this week. If you just stop and think for a second, each one of those pictures is at least $100 million. And for exascale, that number is much, much, much bigger, right? So maybe there's another zero somewhere around there, okay? So that's a lot of money. When the final bill comes in, agonize over this quite a lot. We could do a lot with that kind of money. So if we only get one piece of hardware offered to us, you get one processor, and it costs you $100 million, right? Because there's nothing else you can choose from. Super, super expensive. But if there's 25 people you can pick from, they're going to compete, and they're going to kind of innovate and do stuff that's special for you. So we worry a bit about the competition, and we're trying to get basically the most amount of performance we can spend our taxpayers' dollar on. Having ARM in the mix is another reason to increase competition, and we think we're going to get lots of extra options available to us. But the real reason I think we're here, trying to talk to you about that today, and the interesting stuff we're trying to do at NNSA, is to think about ARM as just an IP company. So a collection of IP where we can get that special workload optimized processor that's going to work just for us. Unless you've been asleep in HPC, you'll know that it's also growing in HPC. Kind of took a little time to get going. It's been kind of slow burner at the back of the hub for a while, but now it's finally moving, right? So we've got stuff in Europe, we've got stuff in Japan, we've got stuff in China. NVIDIA's porting everything to ARM. We've got some new machines coming out Los Alamos that Howard's been working on, and some stuff down at Sandia. And just watch this space, because at SC and ISC next year, you'll see even more. So just take a pause for a second. Let's think about how we bring something like ARM into a program like the NNSA. So if you guys have spent any time at internships at a lab like Sandia or Los Alamos, you've got this super big headache, right? We've got millions of lines of code. It's really complicated. It was written, when dinosaurs were roaming the earth, and we've got to figure out how to bring it to a new platform. Super complicated activity, right? And it's got to really work. It's got to be really good. It's got to be really robust. It's got to deliver the right answer. That piece is actually quite hard sometimes. So you can't just put new stuff down and say, oh, great, here it is, go at it, right? It's kind of complicated. So this is the machine. I'll talk a bit about kind of how we structure this in a second. But so this isn't super big. You've seen all these swanky, thetas and summits that are bajillion petaflops, and everybody's all excited about how many GPUs and everything you've got on all these machines. This one is kind of a little bit simpler than that, right? It's just 2,500, 2,600 nodes, dual socket nodes with ARM in it. The hard thing in this system isn't how do I port my code to run on a GPU? It's, is this even going to work at all? Okay, when I turn it on, and that light goes from red to green, and the node boots, is this going to work? So we don't just put down 2,600 nodes of a machine and just hope that it's going to work. We still spend quite a lot of money on a system like that. So this is what we think about at NNSA. It's a little bit different from Office of Science, where you go to a leadership facility, they've got a massive machine, and it's huge, and you go use that. In our environment, we have these things called ATSE. This is an advanced technology system. It's kind of like a leadership class platform. We've got a CTS, commodity, so this is like the Best Buy, rack 'em, stack 'em kind of cluster. And over here is where our production stuff is all running around. So you've got all our crazy scientists developing new materials and all sorts of stuff. And this is like super robust. It's got to work. When you turn it on, it's just got to go, okay? Over here, this is where I started my career, are these things, test beds. So this is the stuff you turn it on. It might come on, it might not. There might be a compiler, there might not. You spend most of your time writing assembly. The joke here is just sort of, this is for the brave few, right? So probably you guys, if you're sitting in a classroom like this. This is the fun stuff. You get to write papers. Nobody else gets it. But this isn't production, so this is like the Wild West, right? It might work, it might not. So ARM for us started over here, and we spent a long time, we spent basically the last 7 or 8 years working on whether ARM was actually going to work for NNSA in this environment. And in order to sort of get it as far over there on the right as possible in a production environment, there's this sort of gap in the middle where we need to take a mid-step and try and scale it up, okay? So that's what this Vanguard stuff's all about. We'll talk to you about that in a second. So it's not kind of completely production, but it's more production. It's kind of mid-step in the middle. So if you go and you put down ARM, let's just go back to that slide a minute. So remember, super reliable, robust, Wild West, kind of crazy, nothing's going to work. It kind of works on Tuesday, it won't work on Wednesday. This thing in the middle is where our sort of prototype ground is for trying stuff out. So, wheel all this ARM stuff in, big pile of machines. How can we get that working for our production codes? So it turns out that there's no operating system, or there's some operating system support, but not really HPC optimized. There's maybe some MPI routines and stuff like that, but maybe they're not completely optimized. And then there's all the libraries, the I/O libraries and the math libraries and everything else that we need to get working on a platform like ARM. Okay? We have to have that working for our codes to really work. And so we spent a long time working on this. We call it ATSE, it's Advanced Trilab Software Environment. It's basically all the components that you need to bring a production workload to an HPC environment for NNSA. And most of those components are the kind of things that you use as well. So we spent a long time going out, finding what those components are, and we're slowly, one by one, getting them to work on ARM. And that's really what this sort of Astra platform is about. We'll show you some of the performance results of that in a second. I'm going to speed up because I'm going to run out of time. Getting too excited about ARM. So the winning proposal for Astra came from HPE. So this is Hewlett-Packard Enterprise. They're not, haven't been a typical supplier to DOE. And so we've sort of got a new integrator, a new processor, and a new software stack all at the same time. It's quite challenging at times to bring it all together. But this is their picture for all the little things we've got to go off and worry about. So you see all these things where it's got HP and Red Hat and ARM and Mellanox, open source. So there's all these components basically that make up an HPC stack. And we've had to basically step through and validate most of these and make sure that they work on that platform. So every time we do this on a processor we haven't used before, we go through this activity to try and qualify everything. But this is literally the first time we've done that on an ARM platform. So we'll just stop a second and think about what that might look like. So we'll talk about some of the application performance in a second. Howard's going to talk about that. But what we want to think a little bit about is where we're at and what the kind of next wave of this might look like. So I guess what I showed you there was a software stack, and what we need to do is sort of crank forward a little bit for what the next software stack might be. And so we're busy working on this thing called SVE. You heard some people mentioned it today. If you use SIMD vector processing before on processors like Intel or KNL, you're kind of familiar with it. But this is a little bit different. So this is a little bit more like kind of vectors in a Cray sense. So you don't have a fixed width when you go off and program these things. It's sort of anything from 128 bits to 2048 bits wide. And the hardware is somewhere in between that. But the instructions can be, they're kind of encoded that they're kind of length agnostic. It's kind of weird. But very powerful, gives you really good performance. So there's some little pictures over here from ARM on the other side of it. This is pretty drastic change to software environment. So we've been used to working on Intel processors where you know exactly what that vector width is. We know exactly how to get the performance out of that. And all of a sudden, we got a new processor that, or at least we will have an SV-enabled processor in the future with ARM, and we don't know how big those units are, and we don't necessarily know how to get performance out of it. So this is kind of a new challenge. So, you know, lots of people busy thinking about GPUs and accelerators. This is yet another challenge to go and add on top of that for our programmers to think about. So we're busy thinking about that in terms of how we put that into GCC and into this ARM compiler, HPC compiler. We're working with all sorts of people around the world to do that. We're doing a lot of it in simulation and kind of emulators because we don't have real hardware right now. So we've got this system called Astra, and we're trying to run our SVE-enabled workload in an emulator on top of Astra to make sure that all our code is ready for SVE. And so we've got all these plans. You'll hear a little bit about Cocos later this week, I think, and Raja. So these are C++ programming models that you can use to write your code and make them be portable. And we're trying to hide some of this SVE work in there. So it'll be available to all you guys to use. We've seen some huge speed ups. So this is like 6x. 6x is the kind of stuff, you know, the lab president rings me up and tells me I've done a good job. So it's a good week when that happens, right? So 6x is like what I'd like to see. So I can go out on KNL and Skylake and I can get 6x. But the challenge for the group that I work with is how are we going to do that on ARM? We've got to get 6 to 8x as our target. So we're working pretty hard on trying to do that. At the same time, when we're running on ARM, you think a lot of this stuff, oh, it's just going to be there. It's just going to work, right? It's just all this stuff's going to arrive and magic's going to happen. Well, it turns out that that's not true. So go find a machine learning framework that's optimized for ARM. Actually, there is one. Just got published at ISC. But this is super difficult. They're not ready to go, okay? There's new stuff for virtualization if you guys use containers and virtual machines. This isn't ready to go in an HPC setting either, so we're trying to figure out how to make that work. File systems, I can promise you the file systems on ARM are nearly ready. They're pretty good. They're not completely robust yet, so we're still tuning that. And then we're looking at how to optimize a load of other stuff, including MPI. So just because ARM is a standard processor with loads of processor cores doesn't mean all this stuff works. And it's required a load of work to kind of make sure it's really robust and ready for HPC. So let's talk a little bit about, Howard wanted me to explain what this machine is. This is a massive machine called the Z machine at Sandia. We stick things in this machine and we basically blow them up, okay? So if you're interested in blowing stuff up, come work at Sandia. It's fantastic, okay? Stuff just turns to dust when you put it in this machine. It's really neat. There's some great videos online. Go look at it. Z machine at Sandia. Absolutely fantastic. And all of the labs have got these kind of cool toys. They're just great. So I'm going to talk about the processor first. Okay, so ThunderX2 is our implementation of an ARM processor that we bought from Marvell. We said that ARM instruction set can be used by anybody, but we went and we worked with Marvell to deliver the first instance of that. This doesn't look that different on first blush when you look at it and say, oh, well, kind of Intel can do that, can't it? But some of the differences here, we've got more cores and a lot of Intel chips, and we've got, more importantly, more memory controllers. So we're really worried about memory bandwidth. How do we access memory really, really, really quickly? And so this turns out to be one of the things that we're really interested in. And so Marvell had one of the best implementations of that. So just how does it really compare to an Intel chip? So we're here saying, well, we need something else. We want competition, but it's got to be good enough, right? Otherwise, what's the point? So we're trying to show this is good enough. I kind of made this yellow if it was kind of meh, red if it's kind of ooh, and then green if it's, yay. So it's not all good. It's not all rosy. There's a few yellows here, and there's kind of a big red down here for the vector unit today. So we talked about SVE, and that will replace this neon thing, and hopefully it'll be as good as the Skylake over there. But what I really tried to introduce with that was we want processors that are better for various pieces of our workload. And so you don't always want to pick the same processor, right? And so what this table is showing you is there's different choices depending on what you're trying to do. So if you know your workload is really good in a green box, you should go pick that processor. So we're not saying don't pick Intel or always pick ARM or always pick somebody else. We're saying find the right thing for for your workload and go pick that. And we'll show you a little bit about how we're trying to do that next. So just quickly, because I'm running out of time and Howard's going to come and push me off, but
these slides because they give context for the rest.
So you guys have done roofline analysis, I'm sure. This is where you figure out basically how many flops you can load per byte of memory. And this is your theoretical performance, right? So GPUs are at the top, kind of gross amount of compute performance compared to the amount of memory bandwidth you can get. Down here is stuff you can go use on an Amazon EC2 instance, okay? So you can go get your credit card out and you can go get an ARM instance on Amazon. So the processor we've got is right here, this Marvell one, okay? This blue line right here. So it's relatively low on flops, right? It's not that high up in the list, right? But it's, and that's okay for us because we're not really completely bound on compute performance. We want to access memory really fast. And so what we're looking for really is a better ratio. And as you can see here, we're actually, lower in some ways is better if you're not compute bound. So it's a good choice for something like that. I've just marked that here. This is the kind of curve that we want to be on. I talked to you a bit about memory channels. I keep saying we're really interested in really fast access to memory. So just to prove to you that it really is the best way to access memory, there's some stream curves here. We talked about stream bandwidth benchmarks in other talks this morning. So this graph here is looking at Skylake, these two things. This is looking at Haswell, if you guys have run on that. And this is our ThunderX2 plot. And we run it with and without vectorization. So you can turn the vectorizer off, and you can turn it on. So if your code vectorizes, great. Skylake looks pretty good. ThunderX2 is still a little bit faster. If your code doesn't vectorize, you lose a load of that memory bandwidth. Kind of sucks, right? Because you've got to vectorize, and you can't always vectorize your codes. It's kind of hard to do that. So what we want to do is see like very tight bounds on these curves so they can be close together. And we get that with the ThunderX2. And we get the best performance with ThunderX2. We did the same thing for cache performance. Story's not quite so good here. So ThunderX2, gets the green light for memory bandwidth. Cache performance, Intel gets the green light, okay? Intel Skylake's this thing here. So higher is better here. You want really high bandwidth, and you want it as far out as possible. So if you're accessing big arrays, you're going to be out here, and you want your bandwidth to be high. So that's what we've got here with the read and write performance of Skylake. ThunderX2 is this orange line down here. So if your workload is memory bound, good. If your workload is cache bound, not so good. Right? And we'll show you kind of why that matters. DGEN performance, so if all you're doing is just doing loads and loads of math, well, it's about the same as a Haswell. So same kind of color scheme here. This is the ThunderX2, this is Haswell, this is Skylake. If you're really compute bound, go use Skylake. If you're moderately compute bound, this process is going to be okay. And there's one more slide just to show you. So HPL, this is the thing that drives that top 500. Kind of a quick sanity check that Los Alamos has been doing, thinking about these SMT modes. So if you know what SMT modes are, you get multiple threads on a core. Scott kind of talked about that earlier with the KNL. You don't want to divvy those resources up too much by turning lots of threads on. So this kind of shows you what happens. You kind of carve them up too much if you go to SMT4. So you want to stick with SMT1. So let's just recap quickly as I hand over to Howard to talk about the kind of application performance. Memory bandwidth for ARM is good, right? Everybody gives it a thumbs up. Cache performance, kind of, maybe one of those even, maybe a down thumb. Compute performance is kind of okay. So as we think about our workload, we've got to figure out which of those components matters to us the most, and then we can pick the right processor. And Howard's going to talk about how we do that next.
I'm Howard Pritchard from Los Alamos, and I want to present some of the results we have for some mini apps, DOE mini apps, and then some of our real NNSA applications. And I'll be showing results from both, some from Astra and some from some of our other TX2 platforms, including things which would fall into size testbed category, and also from the Cray XC50. So Cy talked about relative performance when you're mostly working out of cache, or if you're working out of DRAM and as far as a kind of a streaming type thing. One other thing you'll see with some of the results, particularly for the mini apps, is also memory latency. So although the TX2 with its 8 memory channels does great as far as streaming accesses. There'll be some cases with the mini apps where you see is because actually the memory latency is better particularly with the Skylake processor, that it comes out on top even for some problems that applications which typically you're not running out of the cache hierarchy. Okay, this one doesn't exactly fit into typical NNSA workloads, but we'll show it anyway. You're probably all familiar with the GUPS random access benchmark, or at least somewhat. What I have here is showing, in the mini apps, we were primarily concentrating just on single processor or single node performance. So for the mini apps, we're always just staying within a single node. What we have here is on the x-axis is a number of, in this case, would be MPI ranks, I believe, for this particular run of GUPS, going up to the max. Oh, I should point out, on Astra, there's slight variations in our systems. Some of the ARM systems we've been using, the TX2s, we have 32 cores per node, per socket, and then, 64 cores per node, and then the others like Astra and also the XC50, it's 56. And in this case, several of these, their focus was just within a single socket. So here, I think we're going up to the 28. And what we see here is compared to Haswell and Skylake, the TX2 is kind of in between. In these runs, we were actually, this was on Astra in its early stages when they were mainly running with just one SMT per core. We would expect that if you ran at 2 or 4, that probably the performance of the TX2 would be a little better because you can get more outstanding loads going per core. The other thing which we haven't tried yet is using larger pages. GUPS is a usual case for using larger pages. And one thing too about ARM, which is a little different from Intel, is they have 2 different kind of modes of using large pages. One is more like in Intel with 4 and 2 megabyte large pages, and the other mode is 64 kilobyte and 512, I think, megabyte large pages. And Astra, I believe, will be running in the 4 and 2 mode, right? Okay. Same thing for our Cray systems. Let's see, I didn't skip LULESH, did I? Oh, no, here's LULESH. Okay, so jumping to a different type of application, we have this and also one of the application results where, in the case of the mini app, this is simulating Lagrangian unstructured mesh hydrodynamics code, and is generally operating out of the cache hierarchy, mostly L2. And let's see. What we have over here is, again, the same. This was from Astra. Higher is better, going out on remaining just on a single socket. Here we see that we can back up here. The Skylake is doing better. It moderately benefits from vectorization. So there are there's the AVX512 and the non-vectorized version. Haswell less so with AVX2. And there's a modest benefit of vectorization on ThunderX2. I suspect with this application, like we've seen when we get to the neutron, one of the neutron transport codes, one other thing about the Intel processor, not KNL, but for the Xeons, it has this enormously deep instruction pipeline. And what I suspect, we have a similar application called Pinnet from Lanel, and what we noticed is there was about a 30 to 40%, it varied some, greater instruction throughput per cycle, like 1.4 versus I think 1.0 for the TX2. And I wouldn't be surprised, I don't remember if this can be run in OpenMP mode or not. I suspect if you could crank up the OpenMP and it was well implemented, that actually the TX2, if you ran it using the SMTs, and I'll show results with the other code that sits out of L2 a lot, it would probably begin to push up towards Skylake. I don't think it would catch up, though. Another code which does something completely different, XSBench, which I think actually Argonne had something to do with. This is simulating one of the significant in terms of computational cost kernels from what's called the OpenMC. It's a Monte Carlo-based neutron transport code, which is used typically for simulating reactor coordinates, so we can figure out how to design that better. And one of the most costly operations there is calculating what we call an average cross-section. And what that ends up looking like, and in this benchmark, how it's implemented is there's about a 6 gigabyte size quasi-structured data set. And the way the benchmark runs is randomly selects a location or material in the calculation of interest and an energy, and it goes and looks up in this data structure all the cross sections for all the materials and nuclides in that section of the reactor. So it has a sort of a random access thing like GUPS, but once you've looked up a particular part in the table, you actually have quite a bit of work to do to process that section of those entries in the table to get an average cross section. And that loop actually can vectorize. So we do see, again, focusing on this single node or single socket performance, there is a substantial benefit to vectorization on the Skylake and some on Haswell, but not on Thunder X2. And so Thunder X2 is here at the bottom, and then Haswell is the middle and top of Skylake. So you might ask, why does vectorization not work here? Well, and we see this a lot when we're trying to see what will vectorize with SVE versus the Neon instruction set. The Neon does not have gather-scatter capability, unlike the AVX512 and AVX2, so it doesn't help. One thing that could probably help XSBench, though, here, so this is all either explicit P thread, no, it's OpenMP. If you ran more OpenMP threads, like maybe 2 or 4 per core, we could probably push that up again just because you'd get more accesses to the table, whereas you're sort of, well, you can maybe try 2 hyperthreads with Skylake, but it probably wouldn't have the same effect. Okay, another Monte Carlo mini app. So Branson is Monte Carlo-based radiation transport mini app, and this is a different way of plotting the data. But again, this one, let's see, this was run on one of the test beds at Atlanta, which has 32 cores per socket. So we have a total of 64 cores in each node. And you see that this is a relative performance thing to Skylake Gold. This code has no vectors in it except some totally useless ones. And that actually is a problem, which it probably is not a subject for today unless you're interested in trying to speed up Monte Carlo-based transport codes on GPUs or SIMD processors, in which case I'd like to talk to you. And what we're showing here is we're comparing TX2, and I'll say a little bit about this, and TX2 using the ARM math intrinsics library versus Skylake Vector, so that's all one. And you notice that we're having a hard time trying to keep up using the TX2 on this application unless you throw all the cores at it, in which case, because they're just 64 cores versus 44 for Skylake Gold, you begin to get on a per node basis pretty close to what you get on a per node for this Skylake Gold. The other thing to point out is the TX2 is much less expensive than the Skylake Gold. So if we normalize this to cost, you'd see a different graph. There's some things too. We haven't optimized the random number generator, which is quite important for this code. And in the future, a lot of both this and the neutron transport codes that we use in our production codes, we need to do something about their vectorization story on SIMD. Now switching to some applications. So Empire is actually just a little, Empire is a suite of plasma physics codes. In the PIC code, which we're showing here, the particle and cell components, just one of, I think, 3 blocks. This is all work by Paul Lin at Sandia. And what we're doing here is we sort of switch gears. Now we're looking at the case of running using larger machines in multiple nodes. So instead of just focusing here, notice the x-axis now is node count rather than MPI rank count or thread count. And what we have here is on the left is timings for the code running the awesome blob. I do not know what makes it awesome. Something must be awesome. But anyway, we comparing it to the Trinity Haswell partition to the Astra TX2 partition. We can run 32 MPI processes per node on the Trinity, whereas 56 on Astra. And they're blocks for a small problem, medium, large, and extra large. And the good news here is that on a per node basis, the performance and the scalability of the code is pretty much the same. You need to be a little careful here because the max run we did for the extra large on Astra was 1024. We went up to 2048 on Haswell. There were some gotchas, turbulence expected for a new system, but that's okay. We'll figure that out. This is the same code, but looking at it differently. Instead, we're looking here at relative performance. And this was a small, medium, and large, and extra large. And notice the node counts, because that will be important for the next slides. And what we see is that, and here we've broken down the particle update part of the code into actually the part where you've calculated the electric field, and you can push the particles, or you figure out the force on them, then you move them, and then you sort the particles, and then there's a linear solver to recompute the new electric field or potential. And higher is better. So we see that for the part that we would expect is kind of memory intensive, which is the sort of the particles, that the TX2 does better. But in general, if you look like at the overall particle update, it isn't doing quite as good as the Haswell. But if you crunch the problem down, so the small one's falling off the radar, but if we started just one node for the medium and 8 nodes for the large, actually they begin to get closer because you're now running more of the problem out of DRAM, out of host memory, and so the TX2 is beginning to catch up. Let's see, we're in good shape. Okay, X-Rage. So this is a key code at Los Alamos. It's a combined hydrodynamics radiation transport code. Unlike the LULESH example, though, earlier with the unstructured mesh, it's Eulerian-based, and it uses adaptive mesh refinement techniques as opposed to the Eulerian, although, as opposed to Lagrangian. And in this problem, we're doing something called the asteroid. Lower is better. And we do have adaptive mesh refinement on. There's no radiation transport, but we're using at least part of the code. These results were obtained on a Cray XC50 using the Cray 9 compiler. If we had more time, I'd talk some about all these compilers. We'll have a brief overview, but there's a whole big topic of discussion there. And here this is a small system. It's only, I think, 170 nodes. But we compare it 8, 16, and 32 nodes, comparing TX2 with 50 processors per node, Broadwell with 48, and Skylake with 56. This code is memory bound for the problems we're typically running, so TX2 looks good. It's the lowest for all the node counts. As is typical when you're memory bound, actually, most of these codes don't benefit from this vectorization because your long pole in the tent is just getting the data into the caches or actually into any kind of outstanding read buffers the processor may have, and not so much the computing on the data. Partisan, okay, I think we have just enough time. This is a different way of computing, handling the neutron transport problem. Rather than Monte Carlo, it's actually deterministic. It uses something called a discrete ordinance method. Important thing here is it's sensitive to cache performance, kind of like LULESH. Unlike LULESH, though, it vectorizes extremely well, both on AVX 512 and Neon, and can be run in mixed MPI open MP mode. I'll have a slide about that in just a minute. It's limited by cache bandwidth. So with this one, we've done a lot of investigation with Tau Commander. It's limited by bandwidth on the TX2s and front end instruction stalls. And this is another plot of relative performance. This time it's only one node again, going from 1 to 32 MPI processes. And you notice because it's working out of L2, Skylake, especially with vectorization on, is much better. This is relative performance to Broadwell vectorized. And at least when you're running MPI only, the TX2 is not doing very well. But, and this is when if you talk to the ARM performance engineers, always there's caveats for everything. They might tell you running your system with 2 SMTs per core is great, and that's what you should do because you're HPC. Well, that's not exactly true. If you actually listen to them and they talk about, well, if you see a lot of front-end stalls, like in your MySQL code, maybe you should do 4 SMTs per core. In that sense, partisan is kind of like MySQL, because what we actually notice is that if you use more OpenMP threads and you run them on the extra SMT units on each core, you actually get a significant speed up in the grind time. Lower is better here. It improves by about 40%. So even though it's not that efficient with the threads, just being able to use them helps. So the main takeaway here is that don't always let people put you in the HPC bucket. I think I'll skip the recon things for purposes of saving time. So at the bottom line, first of all, we've been around more than 2 weeks. So I forgot to take that out. So it's been around more than 2 weeks, Astra has. And in general, compared to the Trinity system, again, this is Trinity, not Skylake, which are a lot more expensive processors. We're seeing a pretty decent speed up on a per node basis for our applications of interest. Now the most useful thing for anyone who's wanting to use ARM systems. Okay, so these are mostly taken from John Linford from ARM's presentations, all condensed down to 2 slides. First of all, if you need to port something to AARch64, you might want to go check this place first to see if whatever you're wanting to work on, like don't waste your time porting OpenFOAM or GROMACS or those kind of things. They've all been there, done that. Also, if it's not here, you may want to double check on SPAC. And I'm assuming that since this is an ECP thing, you're all going to get someone talking about SPAC. If you don't know about SPAC, you need to check with someone, because if you're working with ECP stuff, you should know about that. Another thing, don't use old compilers. If you're using GNU, start with 8, 8.2 or better, 9.1, that's better even than that. Before 8, you're wasting your time, because GNU 8, 7 and older don't know about ThunderX2 processors. You might want to try the Alinea ARM Clang 19.0 or higher. Also, still have enough time. You might consider rebuilding system packages with these compilers, because the ones that come with RHEL and CentOS, I'm not so sure about OpenSUSE, are not targeting ThunderX2. They're targeting a simpler instruction set. Also, if you have a complicated app with lots of dependencies, now is the time to learn SPAC. That will help you a lot. There's training material here, and also there's a cheat sheet here, and I'll point out only a few important things. These flags are important if you're using GNU. This will pick up optimized atomics instructions, which don't come by default if you don't specify. This assumes you're building on TX2. Also, remember, if you like to do your own shared memory programming, ARM is a weak memory model compared to Intel. It can cause all kinds of headaches if you don't have S fences and L fences in the right place. And division by 0 is silently 0 on ARM. Any questions? Oh, someone has a question. Yes?
So you have the MCPU flag. Is there an MARC flag that you use also?
Yes, there is. I don't know why they didn't have it here. If you want to, I think it's Thunder Thunder X299 or something, T99. I knew there was something after that, yes.
So the recommended wisdom is to use MCPU and MTune and not MArch, because MArch is being kind of slowly eradicated from GCC. So they're trying to get people on the newer architectures to change sooner.
Yes?
I just wanted to clarify, when you talk about cost, a couple times, is that cost of like making the processor and buying the processor, or are you talking about the cost like integrated over time given the like electricity bill?
I think it's just the cost if like the vendor made the board with the empty socket and then you had to buy the socket in large quantities and plug it in.
Yeah, I'll just add a bit of nuance to that. So the money that pays for the electricity at NNSA comes from, and you'll laugh when I say this, it comes from a different kind of column in the spreadsheet. So we have a column for buying the systems and a column for paying for the facilities. That's a complicated column, the facilities thing, because you have to pay for people and electricity and everything else and cooling. And so they're sort of split up. What we right now are trying to optimize the procurement cost, but there's a set of restrictions that come from the facilities that mean that the sort of maximum cap of the amount of money we spend there says you can have this much cooling and this much power. So the constraints are applied to what we can do. Over time, we're beginning to optimize those together. So we're beginning to think harder about how to do that, but it's very, very complicated to optimize both of those at the same time.
That is something we're looking at, like with Tau Commander and these other tools. It's fairly easy. On the ARM and the Intel, of course, you can when you run the app, you can find out how much power it used, well, how much energy it used. One thing we notice is that, and that's the reason why SVE is important in the future, is that because you tend to have fewer instructions per cycle for the ARM, the actual cost in terms of energy of a calculation is either about the same for some of them or even more than on like Skylake Gold. But with SVE, hopefully we'll get fewer instructions and more stuff done per instruction. So. Any other questions? Okay, I think we're done.